Hello everyone. In this video we explain acoustics for a quieter vehicle interior, step by step, from the wave equation to Mazda's experimental proof of road noise reduction. Sound is a longitudinal wave. Air particles oscillate through compressions and rarefactions. The wave equation describes this behavior. Absorption converts kinetic energy into heat through viscous friction and thermal conduction, similar to how coastal tetrapods disperse and tire out ocean waves. Using the wave equation with boundary conditions at a wall, we examine absorption. At a rigid wall, reflection forms a standing wave. Pressure is maximum at the wall, particle velocity is zero. On the other hand, at 1/4 wavelength from the wall, particle velocity is maximum. Placing a porous absorber here maximizes absorption. It is theoretical proved. Now look at the measurement results. These measurements show that pressure and particle velocity distributions follow theory. Note the 1/4 wavelength offset between the red curve shows velocity and blue curve show pressure. This underpins absorber placement. Next, let's consider progressive waves, meaning soft boundary conditions. With a soft wall or no wall, reflections are weak, and the progressive wave dominates. Here, pressure and particle velocity are in phase, so the 1/4 wavelength rule doesn't apply, and different absorber strategies are required. Let's compare two different conditions, rigid wall versus soft wall. Under rigid conditions, we get clear nodes and antinodes with a 90-degree phase shift, the 1/4 wavelength shift. However, under soft boundary conditions, pressure and particle velocity are in phase. Recognizing this difference is crucial for absorber design. Additionally, low-frequency waves have long wavelengths. Simply increasing thickness to meet the rigid wall 1/4 wavelength rule is impractical. Therefore, we introduced the two-layer concept to reduce low-frequency waves. One simple two-layer concept is to place an air cavity behind porous material, which creates surface velocity maxima and more dissipation. There are four representative types of two-layer concepts. A. Porous materials plus perforated coverplate. B. Acoustic tile. C. Helmholtz resonator. D. Panel absorber. All of these rely on resonance to increase particle velocity, then damping converts that motion to heat. Now, let's explain an example material. One of the advanced materials in this area is 3M Thinsulate. It is a non-woven material made of extremely fine polyester fibers, with a large specific surface area and high porosity. Thinsulate demonstrates high absorption performance, leading to thin, lightweight, and high absorption in the mid and high frequency bands. It is commonly used in automotive applications like headliners and door interiors. Now, let's see how the automotive industry applies these principles. This is a Mazda case study on road noise reduction. In a tube experiment, Mazda observed unexpected absorption results. With L equals 43 centimeters, the measured absorption exceeded the prediction and was interpreted as a quasi-two-layer effect, with the backing air forming velocity antinodes at low frequencies. Next, a virtual two-layer cabin was modeled based on the results from the tube experiment. In this virtual cabin, SPA reductions around 250 to 500 Hz were observed, showing that changes in the surface velocity distribution contribute to low-frequency absorption. Finally, this two-layer concept was applied to a real vehicle cabin. A two-layer headliner reduced road noise. A softer headliner ensured higher surface particle velocity, which promotes particle mobility and damping. This results in more internal dissipation and a lower SPA than a stiffer design, especially at low frequencies. To summarize, 1/4 wavelength placement maximizes absorption under rigid conditions, but is impractical at very low frequencies. Two-layer concepts, mass spring damper designs, create velocity and reduce low frequencies with thin structures. 3M Thinsulate is effective for mid and high frequency absorption. Mazda demonstrated that the two-layer concept can reduce low frequency noise in real vehicles. Acoustic theory and automotive implementation come together to deliver quieter, more comfortable interiors. Thank you for watching. If you are interested in more details, please click the link to related blog article. See you in the next video.